After discussing proteins, after discussing nucleic acids, and after finally we have discussed lipids, and it's now for the last class of biomolecules for us to discuss, and these are the carbohydrates. Alright, so generally speaking, they are defined as hydrates of carbon. Alright, very informative, right? So that's quite a retarded definition, but at least it gives us the type formula CH2O, because here this is water, hydrate, and this is carbon, that's why carbohydrate. Alright, this also gives us the assumption that if you have n number of O's and n number of C's, you have twice the number of either of the two in hydrogens. Alright, but a more precise definition of carbohydrates, if you talk about structure, is that they are polyhydroxy or polyhydric, meaning there are a lot of OHs, aldehydes, or ketones. So it could be an aldehyde with many hydroxyl groups, or ketones, or a ketone with many hydroxyl groups. So meaning you could classify carbohydrates based on the functional group that it possesses. Alright, so if it has this functional group here, alright, it has the CHO or the formyl group, then you could call that carbohydrate an aldose. So you end with an OSE when you talk about carbohydrates. Now, if you have, instead of formyl, just this one, the carbonyl group or the keto group, you call this ketose. So you retain the OSE. So you use OSE for all carbohydrates again. Now, one thing I would like to mention is that if, for example, I have the same number of carbons in the carbohydrates and they are exactly the same in all hydroxyl groups, alright, such as for this one, what do I mean? Meaning that all carbons have the same configurations, because the hydrogen, when we draw it like this, alright, it could give you the projection of a hydroxyl group being to the right or to the left. For example, this one, this right, left, right, right. This one is, well, there's there's nothing here because this is a double bond. But if we look at the other three, left, right, right, left, right, right, meaning they are the same. And then the only difference is that this is the formyl group here and this is the keto group here. Given that all the configurations are the same and the functional group is different and the number of carbons is the same, an aldose is the isomer of the ketose form. Alright, they are isomers. Now, in the number of carbons, we could also give out particular names. This is just like in geometry, basic geometry. So we have O's for all of that. O's, 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 O's. Alright. For 3, tri, tetros, from tetra, penta, right? Hexa, hepta. So we have this. So we could actually give a complete name to a monosaccharide by giving the prefix for its functional group and followed by the prefix of its number of carbons. So you could, for example, if you have an aldehyde carbohydrate with 3 carbons, you call this an aldo triose, or a ketose with 5 carbons, a keto pentose, right? So in the case of this one, these two have both 6 carbons. These are both hexoses. In this case, this is an aldohexose. This one is a keto hexose. Alright. Now, in the number of units, if it only has 1 unit, obviously we call it as a monosaccharide. If it is 2 to 10, alright, disaccharides also fall under this category. We call this an oligosaccharide, and if greater than 10, we call this a polysaccharide. One thing I would also like to note is that in the presence of these two functional groups, the formyl group would always come at the carbon number 1, because we know that the formyl group is a terminal functional group. It should lie at the end of the molecule, and the keto group is usually at carbon number 2. Alright, you do not see carbohydrates with ketone groups at the middle of things and whatnot. That's why here this is carbon number 1, 2, 3, 4, 5, 6. This is 1, 2, 3, 4, 5, 5, 6. This is an aldose, it's formal group. This one is an aldose, formal group at 1. And this is a ketose, keto group at carbon number 2. By the way, the names of this, just for clarification, this one is D-glucose, and this one is D-fructose. And I just mentioned that if they are the same in everything except the functional group, they are functional isomers. That's why glucose and fructose are isomers of each other. Alright, so we go to the projections. The way that I drew these here is the Fisher projection. They are like you put the carbons in a straight line from top to bottom, and then you write the formulas as this. For the terminal carbon, because it is anyway a primary alcohol, there is no isomerism there, so you could simply draw it as CH2OH. Alright, but since I am a lazy person, instead of using the Fisher, I use the ball and stick. So to indicate the formal group, I use a ball, and then I use a line. Then for this one, this has 3 carbons. This is carbon number 1 with the formula. This is carbon number 2, and at the end it should be implied that this is carbon number 3. So this is the ball and stick version of this one. So if I draw the ball and stick of glucose, it would look something like this. It has the formal group there, and then it has this one faces the right, this one faces the left, and then 2 to the right. Then the terminal is given, so it should be implied. For fructose, however, there is no formal group, so I won't draw a ball here. But there's a keto group here. Alright, I think I'm the only one doing this. I use a double line to indicate the keto group. Then the same as with fructose, left, right, right. So this is the ball and stick form of D-fructose. However, when we deal with non-linear, because these are all linear forms, when we deal with the non-linear form of carbohydrates, and this does happen, I'll explain this one a later on, just after this. The Hayworth projection of the glucose, let's say, is this one. Okay. And this would take a little time explaining, but I'll explain it, of course. So, how did we get this? What the hell's going on? You may be asking, why are carbohydrates existing in the ring structure? Well, in aqueous solution, the linear form of the carbohydrate would actually convert to the ring form. So how does that happen? What's the process? What's the reaction? So I'll explain it here. Let's say that this is glucose. I'll name this. I'll label again the carbon numbers for clarity. So 6 carbons. What happens is that there's a reaction between the functional carbon, the functional carbon, yes, that means here is carbon number 1, and the second to the last carbon. The second to the last carbon, we will discuss later in isomerisms, is named also as the penultimate carbon. So there's a reaction between the penultimate carbon and the functional carbon. So here, what happens is that the OH, the oxygen in the penultimate hydroxyl would serve as a bridge. So how would that bridge look like? So let's draw this again. I lack a hydrogen here. So nothing much change. So this is the penultimate carbon, the one I put here. So what happens is that the penultimate carbon's oxygen would serve as a bridge. Alright? It would serve as a bridge. 1, 2, 3, 4, 5. And you can see that here now the carbon has 5 bonds. 1, 2, 3, 4, 5. So what happens is that instead of this being a keto group, this would now become a hydroxyl group. It will be reduced to that form. So now this would be the ring format or the ring version of glucose. Alright, so how do we interpret this in the Hayworth? How did this become projected in the Hayworth formula as this? So let's count the number of carbons, shall we? 1, 2, 3, 4, 5, 6. the ones that form the bridge are carbon 1, then carbon 5. So if this is the oxygen bridge, this is the oxygen bridge, this is the oxygen bridge. This is carbon number 1, this is carbon number 1, this is carbon number 5. Then this one, this carbon bonded to oxygen, the other one should also be 5. So we could assume that this is 1, then 2, then 3, then 4, then 5. Then you see that the carbon number 6 did not get involved in the ring. It's outside the ring. This is carbon number 6 right here. It's outside the ring. So here, if we count, we have carbon number 1, 2, 3, 4, 5. Then the sixth member is oxygen. The same here, 1, 2, 3, 4, 5, 6, which is the oxygen. So how do we translate now the, I forgot again the OH here. How do we translate these ones, whether the oxygen is, the OH is to the right or to the left? Well, this is what we're going to do. Again, I would like to mention that if you want to use your fingers to demonstrate whether the OH is to the left or to the right, you use your fingers. You exclude the terminal ones, terminal carbon 1 and 6 here, so you focus on 2, 3, 4, 5. So 2, 3, 4, 5. 2 faces the right, it remains there, it faces there. 3 to the left, 4, 5. So this is what we're going to do. If it faces the right, it will project to the bottom in the Hayworth. If it faces the left, it will project upwards. So let's do this. Let's prove. This is for glucose, alright? So this should be congruent. Carbon number 2 faces to the right, it should face down. So it faces down. 3 to the left, right? 3, left means up, left means up. Right? Both both 4 and 5 should project to the right, but 5 here was used for the bridge. So what we're going to focus now is on 4. So 4 faces to the right should go down, so it faces down. So that's how you project it. I hope it's clear, but in case you do not get it the first time around, you may repeat this part of the video. Now, for isomerism, carbohydrates have a lot of isomerism going on, but the first thing we have to know is that they have a lot of isomers because of this, a lot of this. Let's see, carbon number 2 is attached to a formyl group, a hydroxyl, a hydrogen, and then this long chain here. It is attached to 4 different groups, and by now we should be able to quickly process or describe this one as a chiral carbon. Not just this, but also 3, 4, and 5. So how do we count the number of isomers for a particular number of carbons? So the formula to get the number of isomers is 2 raised to n, where n is the number of chiral carbons. So in the case of this one, for a hexose, we have 4 chiral carbons. So 2 raised to 4 means 2 raised to 4, 2 times 2 times 2 times 2 equals 16. So a hexose could give rise to 16 isomers. Alright? Now, we have several types. Enantiomers, Epimers, and diastereomers. There's another type, but we will discuss it later on. Enantiomers, optical activity. How will we be able to know if it is of D or L? Alright, we know already that we have encountered this in nucleic acids, in amino acids. We look at the penultimate carbon. So if the penultimate carbon points to the right, it's D. If it points to the left, it's L. Alright? Just that simple. So for example, this is why we name this D-glucose. Where is the penultimate carbon? It's carbon number 5. And its hydroxyl group faces the right. That's why it's D-glucose. Same here. The carbon number 5 of D-fructose faces to the right. That's why it's D-fructose. So here, for example, we will designate if this is D or L. It's very easy. We just look at this. Right? This. So this one faces to the right, it's D. This one is L. This one is L. This one is D. Alright? In addition, we should be able to identify that an enantiomer or 2 enantiomers must be different in D and L, and then all their hydroxyl groups must be inverted. So if this is right, left, right, the opposite of this must be left, right, left. And this is left, right, left. So this one and this one are enantiomers. How about epimers? Epimers are those which differ in only one chiral carbon. For example, I have here right, left, right. If any of this changes except the penultimate, then that's an epimer. So for example, this is right, left. If this becomes left, left, or right, right, meaning there's a change in any of the two, that's epimerism. And for example, this is right, left, right, 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 right. So the only change is is in this carbon, all right. And then the other two remain the same. That's epimerism. In this case, if this is how many carbons? 1, 2, 3, 4, 5. This is 1, 2. This is carbon number 3. We could say that this one and this one are 3 epimers of each other. Now, if it doesn't fall under enantiomers or epimers such as this is the L version of this one, but it retained the carbon number 3. So you cannot say that's an enantiomer. This is the enantiomer form. You cannot also say this is an epimer. You could also say that this is an epimer, but this is an entirely different isomerism, L. This is of the L isomerism. So, as long as it's not an enantiomer or an epimer, you could safely say that it is a diastereomer. But here, this is actually an epimer, but of a different enantiomerism. Let me draw an actual diastereomerism. For example, this one. Then here, this is a good example of diastereomerism because you did not differ only in one carbon. This is different, right, left. Then you differed at this carbon, and then you also differed at this carbon with retaining this one and this one. Alright?